Problem 1. A 200-gram ball is dropped from a height of 2 meters and reaches a speed of 6.3 meters per second, and then bounces on a hard floor. The graph is a force versus time curve that's triangular. A, is momentum conserved or not? Explain. What type of diagram is appropriate for the situation? An impulse momentum or a momentum bar diagram? Now draw it. What is the average force applied to the ball? How fast is the ball moving after bouncing from the floor? Let's go calculate that. A, let's draw a picture of the situation along with a bar diagram. In this situation, I imagine that we're starting with the ball that starts at some height, and then it's going to reach a speed right before it makes contact with the ground. So it starts off at some speed equal to 0, and then when it hits the ground, we know that it's going to be moving with some speed v1 equal to 6.3 meters per second. So what do we know here? Is momentum conserved? So we want to make our system be the ball. Are there any forces that are external to the ball? And the answer is yes. So if we're looking right before the collision, we could see that then afterwards, they tell us that the ball is going to bounce back. So just by looking at the signs, you're seeing here that the momentum has changed direction. So clearly, momentum has changed. And the reason why the momentum changed is that we had an impulse due to the ground. It's the ground that changed the momentum. So therefore, if I pick my signs as this being negative and this being positive, and by the way, this is after the collision, so then if we ask the same question that we started off with, is momentum conserved or not? The answer is that there is an external impulse by the ground that changes momentum. Right? Since J ground is not equal to 0, that immediately tells us the momentum before and afterwards are not the same. This changes momentum. So now if I start to look at my bar diagram, we could see here that momentum is not conserved. So if I look at my bar diagram, I could imagine that I have a situation where I have, let's say, this amount of momentum. Excuse me, I was wrong. I should have started with the momentum, that this is the momentum coming in. And I'm going to say that this momentum is P1, and you could see that the way I define the momentum of the ball is that V1 is negative, so therefore the momentum of the system initially is negative, but the impulse is pointed in the positive direction. And this is what changes the momentum. So if I compare the momentum before and afterwards, not only do they have the same direction, different directions, but they also have different sizes. So then from my picture of the bar diagram, then it tells us here that the impulse momentum theorem then shows that this is going to be minus P1 plus J of the ground has to equal P2. And that's how it changed the momentum of the ball. Now let's go to B. So in B here, we want to calculate the average force of the ground. So first thing is to calculate the impulse, which is equal to the area. So when I look at that, how do I calculate the area? Well, according to our picture, it's going to look something like this. I have an impulse that starts at 2 milliseconds. It rises up, and then it turns off at 6 milliseconds. And it reaches a maximum force of 1,000 newtons. So this is our force, and this is our time. So the impulse, by definition, has to be the area. So we need this area right here. So when I look at this area, we could then say that the impulse is the area, but the area of any triangle is going to be 1/2 its max height, its height, in this case, it's F max, times its width, which is time. So if I plug in my numbers here, you could see here that this is going to be 1/2 times 1,000 newtons times 6 minus 2 milliseconds. And so if I plug this in, I'm going to get a value for the area that's 2 newtons seconds. And this is going to be the impulse due to the ground. Okay, so now I have my impulse. Well, now that I have my impulse, now I'm going to use the mean value theorem of calculus of integrals. And we don't have to use calculus. What we got to do is that we got to look at the pictures. So if I start with this picture right here, all we have to do here is that we have to get the same areas. So the way we get the same area is that, you know what, let me move this over here. So the mean value theorem says I just need the same areas. So in other words, since this is that of the ground and this is an area, we can get two different areas. We could get the area where I have a triangle, And as long as the area of the triangle is the same, I can choose a second area that is exactly the same area, but has this different shape. So according to the mean value theorem, it just says that the area of the triangle in this case would then equal 1/2 F max times delta T, and this can be the average force, time average times delta T. And you could see immediately that if I compare these two terms, I could come in here and I could cancel out the time, and it essentially tells me that the average force is then going to be 1/2 the max, which will be then 1/2 times 1,000 newtons, which then tells me that this will then be not 1,000. How did I get 1,000? No, it's going to be 500 newtons. And that's going to be the average force right here. So picture-wise, I now look at this thing. If I bring this right here, that if I have the same force versus time curve, that I can have a force that only goes up half as high, and it has the same exact area. And when I have the exact same area, then this guy right here is the average force, which is 500 newtons. So the mean value theorem just allows us to calculate the area slightly different. Let me make sure I make that milliseconds. So now let's go to C. So in C, we want to determine the speed V2 after the collision with the ground, apply the momentum, the impulse momentum zero. And we already wrote that out. We said that this was minus P1 plus J of the ground equals P2. But that, we can then write this as minus mv1 plus J of the ground, and that's going to be equal to mv2. Now, if I isolate V2, you'll see here that I'm going to get V2, then I'm going to get J of the ground minus mv1 divided by m, and I could reduce this by writing this as J ground divided by m minus v1. So now if I put in my numbers, this is going to be 2 Newton seconds. Then this will be 0.2 kilograms minus 6.3 meters per second. And I get that this value is 3.7 meters per second. And that's going to be the speed after the collision.